So let's suppose that we have an object that is moving with a certain velocity, let's say v naught. Now, because this object has a velocity, this object is said to have energy. And this energy is known as kinetic energy. Kinetic energy is the energy of motion. So once again, objects in motion are said to have energy known as kinetic energy. Now, before we define what exactly kinetic energy is in terms of mass and velocity, let's look at the following situation. Let's suppose we have our mass with initial velocity v naught, and suppose we apply a constant net force on the mass m moving with initial velocity v naught and accelerate it over a distance d to a velocity v final shown here. So we're essentially applying a constant net force on our mass over a distance, and that means we're doing work on our mass. So work is a transfer of energy. So we're transferring energy to our mass, and our mass is therefore gaining velocity. Our mass is gaining more kinetic energy. So let's try to figure out how much more kinetic energy our object has at the end than at the initial point. So let's begin by using our formula for work for a constant force. So because we have a constant net force, the work done on our mass is simply given by the following equation. The net work done on the mass is equal to the net force acting on the object mass m multiplied by displacement over which our force acts. Now, let's recall what Newton's second law of motion states. It states that the force, the net force acting on the object is given by the mass and multiplying by acceleration. Now, because we have constant net force, that means we have a constant acceleration. So that means we can use one of our kinematics equations for uniform or constant acceleration. So let's use this equation. So the final velocity squared equals the initial velocity squared plus 2 times our acceleration, which is constant, multiplied by our change in position or displacement. So let's rearrange this equation C and solve for our acceleration A. So we get the acceleration A is equal to v final squared minus v initial squared divided by 2 times our displacement or change in position. And let's call this equation D. Now, let's plug in D into B. So notice in B we have the net force equals mass times our constant acceleration. So let's take this and plug it into our A as we do exactly in this equation. So the net force equals our mass times our acceleration, which we got in this part. And let's call this equation E. Now finally, let's take E and let's plug it into A. So the net work done on our object is equal to net force multiplied by D. So we take this net force and plug it into here. So we get our net work is equal to the mass of the object multiplied by this whole guy, so our v final squared minus v initial squared divided by 2 times displacement multiplied by displacement. So notice our displacements cancel, and let's distribute our mass to both of these variables, and we get the final formula. So, the net work done on our object as we move the mass from this initial position to this final position over a distance d is given by the following equation. So, mass multiplied by v final squared divided by 2 minus mass multiplied by v initial squared divided by 2. So this tells us how much energy our object gained in terms of kinetic energy. So initially, it had one kinetic energy, and at the final moment, it had another kinetic energy, because when we do work, we transfer energy into our system. So it turns out that this is the equation that gives us the kinetic energy of an object given the object's mass and the object's velocity. So this equation, 1/2 multiplied by mass times velocity squared, gives us the kinetic energy of a mass that is moving with some velocity. So for example, let's suppose we have a ball with mass 0.5 kilograms, and that mass, that ball, is thrown from rest and has a final velocity of 30 meters per second. So let's calculate the kinetic energy of the object as well as the net work done on the object. So initially, the object had a velocity of 0. So initially, the object had no energy, no kinetic energy. But after it reached a velocity of 30 meters per second, it had the following kinetic energy. So 1/2 times mass, so 1/2 times 0.5 gives us 0.25 multiplied by 30 squared, so 900, and that gives us 225 joules of kinetic energy. So initially we had no kinetic energy, and then we did work on our object. We accelerated the object to a velocity of 30 meters per second. And so that means if I threw my object, my hand did work on the object, and so I transferred energy. I transferred 225 joules of energy from my hand to my ball, my object. So the net work done on my object is equivalent to 225 joules. And our kinetic energy is also 225 joules.